Hello, this is Paul from Pro Communications and Security Systems, and I'm just demonstrating here a basically signal test via couplers. So I've got 1, 2, 3 couplers. It's an 8 dB, 6 dB, 5 dB coupler. So I've got a 0 dBm signal. It's transmitted at 800 megs. It's coming out, going via the couplers, and then back into the CA5000, and I've got on spectrum analyzer. Now the purpose of this experiment is to look at what happens when I remove a load here, which is 50 ohms. I want to see what happens to the output, which is that, or if I put attenuators in. So I've got a 15 dB attenuator and I've got a 30 dB attenuator. So let's start. So at the moment I've got a 0 dBm signal. On the analyzer, going through the 3 couplers and cabling, we have about minus 6.5 dBm. Okay, so basically what we're looking at is there's a 6.5 dBm loss, for example. Okay, so as part of the experiment we haven't calibrated the system, but we don't need to, because at the moment it's a relative test, which means that I've got this system set up. We've just got minus 6.5 as our reference signal for the system. And really what we want to see is what changes occur when I change the loads on a coupled output. So what we're going to do firstly is I'm going to capture that signal. Okay, so that's fixed now. So we know there's our signal reference, which is minus 6.52. Now I'm just going to select the second trace. Okay, turn it on. Right, so you should see there it's virtually the same. This is trace 2. Okay, so what I'm going to do firstly is I'm going to remove this coupler, terminator on the coupler. I'll just pause it. Okay, so I'm removing that. Alright, now as I've removed that, basically you could say it's an infinite impedance. Now have a look at the output. Minus 6.38. Hasn't really changed. However, for the experiment, I'm going to put in 15 dB attenuator. So I'm putting 50 ohm load on the output of the attenuator. I'm going to put that on the output, on the coupled output. Okay, I'll just tighten that up. Just pause the video. Okay, so that's in now. Let's have a look at the output. Minus 6.5. So relatively no change. So I'm going to capture that. Capture. And going to go to trace 3. Turn it on. Right. So we've still got minus 6.5. So now I'm going to take this off. Actually, for the exercise, I'll leave it on. We're going to go to the second coupler, which is 6 dB. I'm going to remove the 50 ohm terminator. Let's have a look at the output. Minus 6.7. Okay, so it's had some impact. I will put it back on just to confirm. Let's look at that. Minus 6.5. So on a 6 dB coupler, we get 0.2 of a dB change. And that's basically for an open circuit. So now I'm going to put in, this is a 30 dB attenuator, to show you the value. Just put that in focus. Okay, put that in circuit. Alright, so that's in circuit. Let's have a look at the output. Minus 6.5. So, as an open circuit, the reflected signal will actually reflect through. However, the majority of it would go back to the source. And a portion of it, which went that way, had a bearing of 0.2 dB. So now I'm going to add a third attenuator. So just bear with me. Okay, so here's our third attenuator. So this one here, that's another 30 dB. Okay, so I'm going to put that in circuit. Just pause it. Okay, so what we're going to do is I'm going to capture the trace first before putting on the attenuator. So we're minus 6.58. So we're going to hit capture. Okay, we're going to go to trace 4. Turn it on. Okay, so the level is minus 6.58. Right, we're going to remove. We're going to put the 50 ohm terminator on. Just tighten her up, just bear with me. Okay, so I've tightened the terminator. We're putting that on to the 5 dB coupler now. Now 5 dB coupler, we should expect to see a little bit more impact. Okay, and the reason being is because 5 dB, it's splitting the signal, so you get 5 dB through one port and 2 dB or 1.8 dB loss throughput, so it's dividing the signal. Okay, let's have a look. Alright, so our output power is minus 6.59. Wow. So, virtually the same. I'm going to remove the terminator. Just out of interest, let's look at the output. Minus 6.59. Because it's a 30 dB attenuator, even though it reaches an open circuit, you're basically getting 30 dB attenuation of signal. Then a reflected signal will be 30 dB attenuated as well. So therefore, bugger all difference. So if I remove the attenuator, so we've got an open circuit. So basically the signal that's traveled through there, through the coupled port, right, will be reflected. So let's have a look at the impact. Minus 6.39. So therefore, let's say it's minus 6.4. That means we've got about 5 and 4, 0.9 of a dB difference. So the point of this experiment is that DAS installers may be putting attenuators on the output of couplers. However, I think the main reason for that is to balance the output signal, that it doesn't exceed the electromagnetic radiation requirements. But if people are putting attenuators on to balance really low power signals, just to balance the output power of a DAS, I don't think it's actually adds any value. If anything, it's detrimental. But if you've got high power going through these, so for example, if you've got say 33 or 43 dBm of signal, you don't want to be exceeding 30 dBm on the coupled port, then you would put the attenuator. So thank you for watching this video.